Here are some of the diagnostics just to give you a scale for how that works. This is actually called Dante. It has the look of a thermometer. It is a thermometer, except it's measuring the temperature of the target as it goes not to 98.6, but to several million degrees in the first billionth, 2 billionths of a second that we turn it on. So this is how some of the target diagnostics that we have. Now, when we talk about NIF, it's on one level it's a building, but when I think about NIF, it's a huge building. But I look at it as it has only that infrastructure has one purpose: to hold up optics, right, and to hold up a target, and hold it up in a very nice environment. But there were a lot of things that had to be done in order to enable NIF to exist as a laser facility. It is, since I grew up as a laser guy, this is how I still relate to it fundamentally as an optical and laser system. First of all, we had to change the nature of how we made neodymium glass. It's a neodymium laser, but we had to have approximately 150 tons of glass, extremely dry glass, extremely low platinum glass. We run it at around 30 joules per square centimeter. And we had to do a lot of development, and we worked with Hoya and Schott Glass to develop ways to have continuous pore glass. And we have around 3,200 pieces of it in the NIF, and each one of them looks like that. And so when you're piling them up, not only does it have to be very high quality gas, but the whole issues of massive polishing is another issue, and we worked that out with our good friends and partners, Zygo in Connecticut. And we have all of this glass installed in the system right now. We also work with our French colleagues who are building a laser called Laser Megajoule, or LMJ, which is a near sister of the NIF. And this is another thing that people sometimes don't appreciate. NIF is really a part of a great international effort that involves the French, the Japanese, the English, and other countries in a variety of missions. And I think that, which I'll talk about shortly, people don't understand how large a community the inertial confinement fusion community is. It's going on all over the world. It's sort of under the radar screen right now. It's starting, because of Google and other things, it's starting to come out. But I think you'll all be surprised over the next couple of years how big this is, how important I think it is to the laser and optics community because of many of the things that we've developed and benefited from because of that. By the way, everything in NIF is in a line replaceable unit or a cassette. Remember I showed you those 4 laser beams going by? That's how the 4 pieces of laser glass are packed together. And they're being built in a clean room. They're transported and installed in a portable clean room so that the facility doesn't have to be ultra clean, even though the beam line is better than class 10. And when it gets into the beam line, and that's about 2 meters high, you can see this. And also you can see it's flash lamp pumped. If you look carefully, in this hall of mirrors that defines this, you can see where the flash lamps are. There's around 10,000 flash lamps. They're 2 meters high. We store around 300 megajoules of energy when we do this. It's a flash lamp system now. Because of that, the rep rate of NIF is about once every 90 minutes without any cooling. But when we go to, in the future, diode systems, it's going to change everything. In fact, we have built prototypes with glass-type systems with helium cooling that you can fire at a hertz and on the way to 10 hertz on subscale systems. We have a plasma electro-Pockels cell. This configuration of this system is kind of interesting also. This is not a MOPA system. It's one single aperture. And what we do is we multipass through that aperture. And in order to think about this, we're multipassing, multi-tens of kilojoules. And we had to figure out a way to do a plasma electro-Pockels cell. And here you see it. And what we have is a a gas over KDP that we then discharge a voltage across, and then here we can do this with and transmit through that Pockels cell. And these things work extremely well. This is another enabling technology that we had to develop for the NIF. If it weren't for this, there could not have been a NIF. It would have been a MOPA chain. The length of it would have been another kilometer long, and we could not have built it. This thing switches in a few nanoseconds while the pulse is going back and forth, as I showed you. We also had to develop high-gain preamplifiers. You know, there's two basic, there's a basic system, there's a master oscillator that runs at a nanojoule. We come to these preamplifiers, there's 48 of them. They all have to operate together, and they have gains of around 10 to the 9th to the 10 to the 10th. You go up to a joule type energies, and then you go up into those big amplifiers where the glass is, and have a gain of, again, of around 10,000 to 20,000 per beam, times 200 is how you get another million of gain, then convert it to the ultraviolet. And that's that 10 to the 15th gain. I also want you to know that this is not a flamethrower laser. This is an extremely high precision laser, which I'll talk about. Every one of these beams have to be balanced with respect to each other within a few percent over all the beams, every shot, every beam, and they have to be timed within a few picoseconds, and they have to have gains that are maintained in 20 and 50 picosecond steps to less than 1%. We also have deformable mirrors on every single beam. You know, even though we have this beautiful glass, we go through all over 2 meters of gain medium and through or off 100 surfaces on the way to the target. So before every shot, you know, at T-1 second, what we do is have a interferogram picture of this, and you can see we have 39 actuators on this mirror on each and every single beam line, and it brings it up to a few times diffraction limited on every shot for every beam.